per second. And then let's say our final is going to be 10 radians per second. And we're told that this occurs over, let's say, an angular displacement of, let's say, 15 radians. All right. And then we can ask, for example, what is our angular acceleration? Okay. And so we said that, all right, well, the way you approach this, again, is you can really approach this exactly the same way as you would a regular kinematics problem, is that you can always start off, again, just writing down your kinematics variables, right? And then after you've written them all down, you can look at your formulas, right? And so if I look here, I'm trying to find my alpha. I know my angular displacement and my initial and final angular velocities. And so if I go through here, I can see that, like this is probably the easiest one to use because again, I know my final, my initial angular velocities, I know my angular displacement, so I can solve this thing for my alpha, right? And so if we're using omega s squared is omega I squared plus 2 alpha delta theta. This tells us that our alpha is just omega s squared minus omega I squared, right, all over 2 delta theta. So this is going to be, 100 radians squared per second squared minus 25 radians squared per second squared, all divided by 2 times 15 radians per second. Okay. Or sorry, not radians per second, radians, 2.5 radians. All right, so this is what, 75 divided by 15 is 5, 2. So this is going to be, it looks like 2.5 radians per second squared. Okay. Questions on this? Okay. Now, so if you're dealing with purely rotational motion, this covers a lot of it. But the one thing that we did say that's kind of added above and beyond what we had for translational motion is that while I can talk about, again, about the kind of the rotational motion in terms of, like the angular positions, velocities, and accelerations, we could also talk about, for example, for this point here, right, is this point, it also has a kind of linear, right, or, it has translational position, right? Or I should say translational kind of distance that it covers. We can talk about what its kind of translational speed is, what's its tangential acceleration, all right? And so we said that there's actually then this kind of nice little places where we kind of link these two things, is that it turns out that if I want to kind of look at, what is the kind of distance that I'm covering, right? Then what I can just look at is if I look at, again, what my angular displacement is, if I multiply that by r, then that effectively tells me kind of how far I've actually moved, all right? And then we have a similar thing here, is that, right, for my v, right, this is basically r omega, right? And then similarly for my tangential acceleration, this is r alpha. Okay. And now it was important to remember that, again, this expression here, r times alpha, whereas here, for example, this is just my speed, right? So again, you can think about this as this is tangential speed, but again, we know that speed is always tangent, right? Speed is always tangent to your path, and so this is really kind of the entire speed or velocity that we're dealing with here, okay? But with acceleration, again, it's a little different. So we're going to have both tangential as well as centripetal acceleration. And so for my centripetal acceleration, well, this is still v squared over r, but we can also write this in terms of our angular quantities because we know our v is r omega, so this is r omega squared over r, so this is r omega squared. Okay, and so when we're dealing with kind of purely rotational motion, right, I also have these kind of quantities that I can deal with where I can kind of link the kind of translational movement of points on my object